Okay, so today we're going to quickly talk about some concepts for electric field before I do a sample problem for you. So electric field is how charges feel each other. So remember, we said that there's a force on a charge due to any other charge, no matter how far away it is. So how does it know the other charge is there? Well, the answer is that there's something that's called an electric field that stretches out in space like an aura that surrounds every charge. And so if I put a charge at point P, it's going to get either attracted or repelled by that charge at Q, depending on whether the charges are both positive, both negative, or one's positive and the other's negative. So what we do is we talk about a small positive test charge. So if you look at the black dot here in figure A, we assume that that's a positive test charge. And if we put that in an electric field, it's going to feel a force in the direction of the electric field. So the electric field, which we call E, is the force on a small positive test charge divided by the charge. So since the force is equal to K Q1 Q2 over R squared by Coulomb's law, if I divide that by the small charge Q, if I put the Q in the denominator and divide it, I get that the electric field for a point charge is just KQ over R squared, where that Q is the charge that we're getting the electric field from, and R is the distance that we are away from the field. The force on any charge in an electric field is just equal to the electric field times the charge. And if it's a positive charge, then like in figure B, the force is in the same direction as the electric field. If it's a negative charge, then the force is in the opposite direction to the electric field. We can represent the electric field by field lines, and the field lines are in the direction of the force on a positive charge. So if I put a positive charge near another positive charge, it's going to get repelled away. So no matter where I put a positive charge near another positive charge, I'm going to feel a force that's going out away from it. So we said the electric field lines come out of a positive charge. And if I put my positive test charge near a negative charge, like in figure B, it's going to get sucked in, it's going to get attracted. So the electric field lines go into a negative charge. So remember, field lines come out of a positive charge and go into a negative charge. The number of field lines in an area at the charge is proportional to the magnitude of the charge. So if you've got a bigger charge, then the field will be stronger and the lines will be closer together. So if I look at the picture down on the bottom here, close to the positive charge and the negative charge, you can see that the field lines are close together. And so that tells you the field is stronger. And when I'm halfway in between, the field lines are further apart. So that tells us the field is weaker. At any point in space, the direction of the field is tangent to the field line. So you can see, and again in the picture here at point P, the electric field is along a line that's directly along that electric field line, no matter where the field line is. And electric field lines never cross each other. This picture here shows a positive charge and a negative charge with a distance in between them. And we have a special name for that that's called an electric dipole, where you have two equal and opposite charges. So let's quickly look at a couple of important concepts before we go on and do a problem. So if I have that negative charge sitting there, the blue dot, and I'm at the position of the black dot there in space, what direction is the electric field at that black dot? Well, what we do is we imagine that that black dot has a positive charge on it. And we think, what will happen to that positive charge? Well, that positive charge is going to get attracted to the negative charge. So the electric field is going to be in the direction of B. Another kind of question you might be asked to do is to do some manipulations of the equation. So remember, electric field is KQ over R squared. We only have one Q here because it's just the field due to a charge. So let's say that we're sitting a certain distance away from my charge. So here's my charge. I'm a certain distance away from it. And I measure a field E0. Now if I take it and I make my charge twice as big and I make my distance go also twice as big. So then my question is, what's my new electric field? Well, what I do is I put into the equation 2q in the numerator, and the denominator, instead of r, I put in 2r, and I got to square that. All right, so what I get there is k times 2q, and on the denominator I'm going to get 4 times r squared, because 2 squared is 4. So what I'm going to get is, I'm going to get kq over 2r squared, and my E0 was kq over r squared. Now I've got kq over 2r squared, so my new electric field is half of the old electric field. So the answer is D. Make sure you're comfortable with doing things like that, where you change the charge, change the distance, what happens to the electric field. And if you're not comfortable with doing it algebraically, you can just assign a charge. So you could say here Q equals 1, and R equals, I don't know, say R is 2 meters. And here I go from Q, have Q is 2, and R equals 4 meters, and just put in the numbers and see what you get. Just like the electric forces, if you've got more than one charge, the electric fields will add together. And so if you remember, we did a question like this for electric force. What was the direction of the electric force at the dot? Well, if I look at the direction of the electric field comes out of the positive charge and it goes into the negative charge. So the electric field is going to have a component both to the right and to the left, and we have to think about which one's going to be stronger. Well, the electric field is kq over r squared, and that r is different for the two charges. It's bigger for the positive charge, so that means the electric field from the positive charge is going to be smaller than the electric field from the negative charge because it's further away. So that means that if, imagine you're having a tug of war, the negative charge is going to win. So that means that the net charge is going to be over towards the direction of the negative charge, and so the net field is going to be in the direction of arrow B. All right, question regarding field lines. When we have a picture of field lines like that, at which point is the magnitude of the field the greatest? Well, remember we said when the field lines are closest together, that means it's biggest, so the field lines are biggest at point A. Regarding force, remember electric field and electric force are both vectors. The force is Q times the electric field. A positive charge feels a force in the same direction as the electric field. So that positive charge is going to feel a force that's going to accelerate it upwards. So as a function of time, that velocity is going to go from being straight horizontal to having an upwards component. And of course, the longer you wait, the more upwards component there'll be. So if I waited a long time, it would get to B. All right, last concept. So I've got two balls. One of them has a charge of plus Q, and one of them has a charge of plus 4Q, and they're separated by a distance of 3R. So the question is, where on the line between the two charges is the net field going to be 0? So remember, I'm going to feel a field coming out of each of the positive charges towards the center. Okay, so what I want to know is where on the line between those two is the net field going to be 0? Well, the electric field, let's call this charge 1, is going to be kq1 over r1 squared. And q1 is just q, so let me just put in q. The electric field from this one is going to be k times 4q over r2 squared. So if I want those guys to cancel out, they've got to be equal to each other. All right, so if they're going to be equal to each other, that means that kq over r1 squared equals k times 4q over r2 squared. And just by common sense, you know that it's going to be a smaller electric field from Q than from 4Q, so you need to be closer to Q than to 4Q. So if the two charges were equal, then the fields would be equal at position 3, but I've got to move closer to the charge 1, the plus Q, in order to get them equal to each other. And I can do a calculation if I want. So let me see, I can cancel out things that are equal on each side. So what I get on this side is 1 over R1 squared equals 4 over R2 squared. Cross multiply the denominators. So I get R2 squared is equal to 4 R1 squared. Take the square root of each side, and I get R2 is equal to 2 times R1. So what that tells me is that the distance that I'm away from the big charge has to be twice the distance that I am away from the small charge. And so that's going to be at position 2. At position 2, I'm going to be 2R away from 4Q and R away from 1Q. And again, go through the math if you need to understand this. All right, so let me do a quick question. So what's the net electric field at the origin? So remember, it's going to be vectors. I'm going to have to add them together. And what would be the acceleration of an electron that's placed at the origin? So what I want to know is, what is my net electric field at this position here? So let me first start off. Let me number these so we can talk about them. So I've got field 1, field 2, and field 3. And we're going to do the same thing that we did when we talked about electric forces. Going to go through the same steps. So first, draw the arrows. So the electric field goes out of a positive charge. So E1 is going to come out of charge 1. Goes into a negative charge. So it's going to go up into that charge there. And it's going to go into charge 3, which is negative. So we've got two charges going towards the right and one field going up and two fields going to the right. So now let's calculate the magnitude. So E1 is going to be K Q1 over R1 squared. K is 9 times 10 to the 9. Just like it was before. Q1 is 2 microcoulombs, 2 times 10 to the minus 6 coulombs. And R1 is 0.2 meters. I'm going to square that. So E1 is 450,000. And the units are newtons per coulomb, or we'll learn next chapter, also volts per meter will work. E2 is going to be K Q2 over R2 squared. And I'm going to ignore the sign of the charge, the direction I'm just going to think about. So I'm going to use a charge of 5 times 10 to the minus 6 for Q2. And the distance again is 0.2 meters. Square that. And I get a big number, 1,125,000 newtons per coulomb. And finally, E3 is K, and again, absolute value, Q3 over R3 squared, 9 times 10 to the 9, 3 times 10 to the minus 6, over 0.2 squared, and I get 675,000 newtons per coulomb. Okay, so to get the net field, now the next thing we do is we put the components of these. So if I think about this, E1 is in the plus x direction. E2 is straight up, so that's in the plus y direction. E3 is also to the right, so that's in the plus x direction. So my net field In the x direction, I'm just going to add the two x components. So it's going to be 450,000 plus 675,000, which is going to give me, coincidentally, 1,125,000 newtons per coulomb to the right. And in the y direction, I just have E2, which is also 1,125,000 newtons per coulomb. Okay, so how do I get my magnitude of the net field? Well, it's going to be square root of x squared plus y squared. And so if I put in for each of them 1,125,000, then I get 1.59 times 10 to the 6 newtons per coulomb. What's the direction? Well, for the direction, I choose a different color now. So I've got 1 million going to the right, 1 million going to the left. If I add those two together, I get that my net electric field is going up and to the right, and it's at 45 degrees. If I want to calculate what it actually is, I can do, let me see, move over to the bottom here at the right. Tan theta is EY over EX, and they're the same, so it's just going to be 1. So theta is inverse tan of 1, which is 45 degrees. So if they weren't equal, that's what you would do. If they're equal, you can just say, okay, by inspection, I can look at it and say that's going to be 45 degrees. All right, so what's the force on the electron? Let me see. I'm going to see if I got enough room to do it up here. All right, so the force is the charge times the electric field. So I need to go and look up what's the charge on an electron. Q for an electron is 1.6 times 10 to the minus 19 coulombs. So the force on the electron is going to be 1.6 times 10 to the negative 19 times our electric field, which is 1.59. And sorry, I wrote that down wrong. That's 1.59 times 10 to the 6 newtons per coulomb for my net field. All right, so if I do that, you can see I'm going to get a very small number because I've got 10 to the minus 19 times 10 to the plus 6. The force on the electron is 2.54 times 10 to the negative 13 newtons. And the problem actually asks me what's the acceleration. So acceleration, remember way back from physics 1, F equals ma. So A is equal to the force divided by the mass. So we have to again go ask Mr. Google, what's the mass of an electron? The mass of an electron is 9.31. So 9.11 times 10 to the minus 31 kilograms. So the acceleration is F over m, 2.54 times 10 to the minus 13 over 9.11 times 10 to the minus 31. And I get a very large force, 8.8 times 10 to the 14, a very large acceleration, meters per second squared. All right, so that's a very big acceleration from a very small force because the mass of the electron is so small. Okay, what would the direction of the acceleration be? Well, remember, an electron has a negative charge, so the acceleration would be opposite to the electric field, so it would be down and to the left. Okay, so we add electric fields just like we added vectors. And so what I want you to do today for your active learning problem is to calculate what's the direction and the magnitude of the net electric field at the center of the square. And they're told that the sides of the square have a length of 1.0 meters. Okay, so you need to calculate at the position of that dot at the center of the square, what's the net electric field due to those two charges, a plus 2 microcoulombs and a minus 2 microcoulombs. And remember to start by drawing the arrows for the direction of the electric field, and that'll help you figure it out.